Hello, I welcome you all in this lecture related with the failure analysis and prevention. And we are talking about the failure analysis of the form products. We have talked about few aspects related with the fundamentals of farming and the issues related with that. In this lecture, initially I will be talking about few more issues and the problems which are created during the manufacturing of the metal by the forming processes, and thereafter we will be taking up one case study related with the rolling process. So, what are the common causes which lead to the failure of the rolling and then failure of one particular component of the rolling that will be taking up. So, the failure of the guideways apart from the fundamentals we will be talking about the failure of the guide piece in the rolling mill, basics of the wear, because mostly the failure occurs by the wear, then important factors that affecting the wear, structure properties, case studies related to the failure of the guide pieces, failure analysis procedure, finding observation and strategy to avoid the failures. So, here the issues in the metal forming, like the formed products experienced some kind of the damage, like say initially the metal will be maybe in very good uh, condition with the second phase particles here and there well distributed with the good bonding. But when it is subjected to the severe plastic deformation due to the difference in mechanical properties of the particle and matrix, the particle matrix interface experienced a lot of strain, and therefore, the particle matrix interface shows the voids. The void formation, once the voids are nucleated, then they will grow and their coalescence will lead to the crack and their growth eventually will lead to the fracture. Okay. So, whenever there is a severe plastic deformation of metal having the hard particles in the matrix of the soft metals, that leads to the interfacial damage. Particle matrix interface is damaged in form of the separation or the void formation. Okay. This damage induced in these formed products affects the service performance under the variety of load conditions. Okay. So, especially under the shear and under the tensile loading conditions in presence of the void, these voids. So, under these kind of the stresses and loading, voids nucleated during the forming, they tend to grow and eventually their coalescence leads to the fracture. Increasing tensile hydrostatic stresses promotes the void formation. So, if we have needle shaped particles or the circular shape, in all the conditions this kind of the void formation can take place because of the differential properties of the particles as compared to the matrix subjected to the common plastic deformation. So, increasing damage is induced by the plastic deformation in the material, and that can appear in form of the crack at the center, say. So, we may have like this kind of the center crack may reflect at the surface, or around these second phase particles there can be void formation, also pore formation. Okay. And inclusions, especially hard, brittle, non-metallic material inclusions, also promote this void formation and the related cracking. Okay. So, if we see, when a material has been subjected to the severe plastic deformation, it experiences a lot of undesirable changes, especially under the low temperature condition. So, increasing the ductile to brittle transition temperature, say usually materials may show very good the toughness, say at a high temperature, this is say 0 temperature, this is high temperature and this is low temperature side. Okay. So, at high temperature, metals show very good toughness and ductility, but as the temperature comes down below certain level, the toughness and ductility are compromised very badly. So, this change in behavior of the material is quantified in terms of the toughness loss. Okay. Material absorbs lot of energy for, during the impact test at a high temperature, but it loses the energy requirement significantly when the same material is subjected at low temperature. So, we say that this kind of the change in the toughness of the material with the drop in temperature is important Okay, and this particular temperature zone of temperature or range of narrow range of temperature over which such sharp drop in in toughness is taking place, that is termed as the ductile to brittle transition temperature. So, obviously we will see here there is a range of temperature, we can use median if it is not very sharp. So, there are multiple aspects which will be affecting this trend of variation, because for some metals this trend is very sharp and for some it goes very gradually. Okay. So, most of the FCC metals, they experience the gradual drop, okay, while BCC metals experience the sharp drop in the toughness with the drop in temperature, especially across this ductile to brittle transition temperature. Okay. So, why I am talking, because when the metal is subjected to the plastic deformation under the low temperature conditions, this ductile to brittle transition temperature is shifted on the higher side. So, if it comes near the ambient condition, then it makes the material brittle even at the room temperature. Material which could have been, which was the ductile, will behave like a brittle material if there is an increase in the ductile to brittle transition temperature. So, it is always preferred that this ductile to brittle transition temperature is low. Increasing carbon content increases the ductile to brittle transition temperature, while addition of nickel and manganese reduces this ductile to brittle transition temperature. Another undesirable effect of the metal forming process is the embrittlement, which reflects in form of increased yield strength coupled with the increased hardness, but loss of toughness. So, this makes the material very sensitive to the crack, because if the material is hard, material is brittle, of low ductility, then it cannot tolerate the notches and the cracks and defects if they are there in the material. Okay. So, the nose sensitivity is enhanced. Now, the next point is the metallurgical heterogeneity, which is commonly observed especially in cold form products. It is possible like surface layers are severely strained as compared to the middle portion, and therefore, the relevant changes in the material characteristics that will be more dominating at the surface than as the core. As we can see in this diagram also, here in the core section, the change in the grain structure is almost same, is negligible, but near surface layers they are subjected to the severe deformation and straining. And because of this one, what we will notice, like if we try to measure the hardness distribution from surface to the core from point A to point B, then the typical trend of the variation observed is like this. So, this higher hardness is attributed to the work hardening or strain hardening of the material. If the material is subjected to the continuous blows to achieve the desired shape and size, especially in the drop forging, then the surface, jarred surface or very rough surface is achieved, which will can show the tendency of the chipping of or spalling of the material. Loss of toughness and ductility, about that I have already talked, like this will be reducing the tolerance to the defects. So, the damage tolerance to the defect is compromised because of loss of toughness and ductility. So, the damage tolerance is reduced. Okay. Anisotropy is again like the variation in properties of the material from one side to another, okay, from one zone to another. So, that is what we can see, the grains, the metal may be stronger in one direction as compared to the other direction, or the in the different zones material may show the different mechanical properties. Okay, this is what I was saying, like if the deformation is being done slowly or at a faster rate using the low rate of loading or high rate of loading, accordingly we get the difference in the behavior of the material. When the low rate of loading is applied, material shows the lower strength and the greater ductility as compared to the case when it is subjected to the higher rate of loading, it will be showing the higher strength but reduced ductility. This is about that embrittlement being occurring due to the drop in temperature, which I have described just now as a ductile to brittle transition temperature. For FCC metals, the drop is very gradual, but for the BCC metals, this drop is very sharp. So, if you see there is a range of temperature, so we prefer to use this median temperature value across which this drop is taking place. So, in the left side the material behaves like more like a brittle material, on the right side means at high temperature condition it will be behaving like a ductile material. So, if we take extremely high strength materials, then see the drop is again gradual. The damage tolerance is about like if there are lot of say if material is having the lot of inclusions. So, here say the volume fraction of the inclusions say 0.5, 1, 1.52. So, if we are having the increasing fraction of the inclusions, then the material's ability to elongate, this percentage elongation is compromised and it happens like this. So, if the material is having very less percentage of inclusions means very few matrix second phase particle interfaces, the ductility will be more, otherwise it is compromised very badly. When material is not subjected to any deformation it is fine, but when it is subject to severe deformation in presence of these second phase particles, few voids and cracks will be nucleated, then they will be growing in the size and eventually their coalescence will be leading to the suppression. Okay. So, now if we say that the rolling is one of the bulk deformation process. Okay. Rolling is a bulk deformation process. We know that it uses the two rolls, it can, there can be multiple situations where two rolls and between that the material is forced to pass through to cause the plastic deformation. So, it reduces the thickness while width remains constant. Okay. So, this is the kind of simple rolling process. So, there can be like two roll milling rolling stand or 3 or 4 high rolling stands. So, depending upon the number of rolls the different categories are there, but that is not the purpose of talking here. What can lead to the failure of the rolling, like material is not getting rolled. So, these are the various things or various ways by which the failure during the rolling may occur, which may be in form of like jamming, okay, collaring, slipping, pulling and piling up of. Okay. So, jamming means the system has jammed and the rolling is not happening, like too thick incoming rolling stock or the distorted stock or the rollers, very large inter-roll gap, incorrect inlet guide which is very toot or tight or very loose, skewed guide, they have not arranged and installed properly, very low temperature stock resulting in very high yield strength and the low ductility, or the system failure in form of like the failure mechanical or electrical failure. So, system is not running, so how it will work. Collaring is about like the sheet which is being rolled is wrapping around the roller. So, stock wounding circumferentially on the roll, large difference this can happen due to the large difference in the roller diameter leading to the variation in the upper and the lower rollers. So, large difference in roller diameter leading to the upper and lower pressure variation, or large gap between the contact guide and roller and the misplaced guides. So, these are a few regions which are related with the collaring. Piling up means the incorrect rolling speed, means one is stand is rolling at a higher speed than the other, things are not synchronized, and or the power fluctuation means at one stand the rolling is still going on while at other rolling stand it is not going in the same way due to the fluctuation in power, then it will be leading to the piling up of the rolled sheets or the difference in stock temperature in the different zones. Pulling is the another situation which is about like observed in case of the continuous rolling. So, absence of the synchronization of the rolling speed, that can lead to this kind of situation, and then a downstream flow speed is more than that of the adjacent stand. So, this can also lead to the pulling, and the tensile stresses being developed due to the pulling can lead to the elongation and the breaking of the material. Then slipping is the another scenario related with the failure of the rolling. So, slipping of the stock, slipping between the stock and the rolling material, or no rolling phenomena happening when the slipping occurs, incompatible section thickness or the roll size or the higher than the acceptable bite angle or incorrect rolling line. So, these are the few common failures and the bigger causes related with that. So, when the rolling is happening, what happens, like there may be a kind of the furnace where from material is heated, then this material is guided with the help of the guide pieces, and then it will be passing through the rolls for the rolling purpose. So, what happens, these guides are supposed to feed the stock material to the rollers in very aligned and perfect manner, so that it is rolled effectively. Okay. So, that is what we can see here. The roller guides are the guidance devices for producing the steel bars and slab products from the steel using the heating, but steel which is coming from the heating furnaces. Okay. So, it comes at a high temperature, say at 1000 degrees centigrade, then it is passed through the roller guide and followed by the through the rulers. Okay. So, it is expected that, like, between the rulers and this one, the bars, the friction is minimal and preventing the seizure and reducing the abrasive marks. Okay. This is particularly used when the process is continuous. Rolling is done subsequently in number of stages. So, the process line of the steel rolling, this is where it is used, and whenever it works, like, the hot bar will continuously be guided by these guide pieces. So, the guide pieces will be continuously in contact with the steel bar which is to be rolled. They will be at a high temperature. So, there is a continuous contact of the guide pieces with the bar at a higher temperature, that too at a high speed. So, the temperature depending upon the metal of the bar can be around 1000 to 1100 degrees centigrade, or the guide pieces temperature accordingly may go up to say 600 to 800 degrees centigrade. So, a material must be able to sustain these high temperature conditions, especially when a steel bar is moving at very high speed of say 5 to 10 meter per second. So, if that is the case, then these are very severe conditions as far as operation is concerned, and the guide pieces under such severe conditions tend to get failed. So, because there is a heat and there is a continuous rubbing of the bar. So, this leads to the thermal fatigue. This is one, and there is a continuous wear of the material. So, to maintain the temperature of the guide pieces also, sometimes the coolants are used. Okay. These coolants, if not cleaned or very acidic in character, then they will interact with the guide pieces and form the corrosion products. These corrosion products eventually will be leading to the wear of the material from the guide pieces. Okay. So, it is important to understand that these hostile and very severe working conditions make the survival of the guide pieces very difficult, and therefore, the guides fail due to the thermal fatigue, impact fracture, because the speed of the wire which is coming across these guide pieces is very high, will be leading to the impact as well, and the wear. Okay. So, wear is the material loss due to that will be happening due to the abrasion, adhesion, fatigue wear and the corrosive wear. Okay. So, what is this? Like, say, when the metal to metal contact is taking place at a high temperature, say speed is 6 meter per second, temperature is 800 degrees centigrade, and there is a continuous rubbing and movement, then this metal to metal contact leads to the continuous rubbing under the pressure. Okay. So, this leads to the adhesive wear situation. When there is a adhesive wear situation, there will be mixing of the metal on the two sides, like the guide material, say cast iron, and steel material on the other side. So, the continuous mixing and the mechanical mixing forming a kind of layer both the sides. Since the guide is fixed, steel is moving continuously. So, one typical layer is formed near the guide surfaces, which is very hard, brittle and sensitive to the crack. and because of this continuously the material in form of the wear debris will be removed. This is an example of the adhesive wear. In addition to that, things are working at a very high temperature. So, the cast iron and steels, they will be getting oxidized. So, these oxides, iron oxides, these particles will also be coming in between the guide and the bar which is moving at a high speed. So, if these debris of the oxides are coming in between the guide surface and the steel, then this will be leading to the 3 body abrasive wear. Okay. So, 3 body abrasive wear means our abrasive particle has come in between the guide and the bar which is moving, leading to the abrasive marks on the surface. So, abrasion is the another common cause of the wear of this kind of the guides. Adhesive wear and abrasive wear, these are the two things which will be contributing. Since the roller, if you see, the roller is continuously, guides are continuously, say guides are there and material is continuously moving. So, these experience the like say the fatigue conditions. So, due to the fatigue, the thin layer of the material is removed in form of like chipping. So, the cracks nucleate under the fatigue conditions below the surface, and then they grow, and their coalescence ultimately leads to the removal of material in form of fine chips. Okay. So, these fine chips, removal of the fine chips again will be causing the loss of material from the guide surfaces. In addition to this, since the coolant is being used for controlling the temperature, if the coolant is acidic in nature, then it will be reacting with the metallic surfaces of the guides. So, when the coolant is acting and reacting with the surface of the guides, so it will be forming their reaction products. Okay. Reaction products between the say cast iron in this case and the acidic thing. So, they will be forming the reaction. These reaction products are usually softer, and since there is continuous rubbing of the steel bar, so these soft products will be removed easily, and that will help in removing the material from the surfaces. So, that is how the adhesive wear, abrasive wear, corrosion wear and surface fatigue wear, these 4 types of the wear are responsible for the removal of the material from the guides, and when the material is continuously removed from the guide pieces, they lose their shape, they lose their size, and the loss of change in shape and size makes their functioning difficult, which may not be able to guide the bar directly and properly into the rollers for the rolling purpose. Okay. In addition to this, the thermal fatigue is another important aspect. Like in thermal fatigue, what happens? The guides are subjected to the continuous heating and cooling. So, continuous heating and cooling leads to the expansion and contraction. So, this leads to the situation of the thermal fatigue, and in thermal fatigue there will be chipping, there will be spalling of the material from the surface, and the loss of material from the surface that will be leading to the failure. Okay. And another important thing, since the wire is coming at very high speed and it will be impacting the surface of the guides. Okay. So, this impact also leads to the fracture. Okay. So, impact, fracture, thermal fatigue related damage, these two types of the damages make the guides unrepairable. Okay. So, if the guide has been damaged due to the continuous thermal fatigue and the impact conditions where the fracture has taken place, cracks have nucleated due to the thermal fatigue, they make the guides unrepairable. Okay, and we need to replace. But if the material loss is taking place simply by wear and leading to the failure, probably this can be repaired. Okay. So, the important characteristics, because the guides are subjected to the loss of material by the adhesion, abrasion, surface fatigue and the corrosion. So, the mechanical properties and metallurgical properties all will be affecting uh, the wear behavior of the material. So, hardness is one of the important property, but not at room temperature. It is important that material must have the hardness at a high temperature. If it does not have, then it will lose its resistance to the wear. Strain hardening behavior, at high temperature certainly material will not be experiencing the strain hardening, but will be experiencing the softening. If the metal gets softened easily, does not get hardened, the hardness is lower at a higher temperature, then at elevated temperature, especially under the high temperature conditions under which the guides will be working, the material will not be able to survive effectively. The grain size, shape and distribution, the fine grains and the well equexed grains, the type of phase, see if there are hard and stable phases are there in the matrix, then they will resist the thermal softening, they will maintain the hot hardness, they will resist the wear which is happening. So, it is very important that material is having the desired hot hardness and desired thermal stability, so that it can resist the wear under the hot conditions. Okay. And additionally, the conditions under which sliding is taking place, the kind of the normal pressure, the speed, the temperature at which it is happening, and the lubrication or the coolant if it is being used for reducing the related wear. So, in this particular case study, as I have said, the guides were made of the cast iron through the and which was treated for the quenching in order to achieve the hardness of the HRC 63. And under the operating conditions, the guides were working at the temperature range of 600 to 800 degrees centigrade, and the process line was serpentine, means the when the bar was passing through the rolling bar was passing through the guides, it was like there were high chances of the impact. Okay. The steel wire was being rolled, was subjected to the heating of the 11 heating in the range of 1100 to 1150 degrees centigrade, and it was moving at the speed of the 6 meter per second. Okay. So this was the guide made of cast iron of the given hardness. This was the temperature experienced by the guide during the operation. Okay. And this was the metal which was subjected to the rolling and moving at this speed at this temperature. So, investigation was carried out and it was found that guides primarily failed due to the loss of material happening due to the chipping. Okay. This loss of material led to the change in shape and the dimensions, and this was also caused due to the reaction products being formed by the coolant during the operation, and these reaction products were getting removed during the operation. Okay. See, all these things led to the loss of material and the loss of the shape and dimensions of the die, which led to the failure. So, the failure occurred due to the wear, multiple reasons were there, multiple mechanisms were working, misalignment. So, it is better idea to have good control over the mechanical properties, especially which can sustain the operating conditions, especially because the carbon steel or cast iron will not be offering reasonably good hardness at elevated temperature. So, 600 to 800 degrees centigrade is really very high temperature, and cast iron is not expected to offer very good hardness at elevated temperature, maybe very good at room temperature. Okay. And the presence of the carbides like iron carbide and other kind of carbides in mm, the cast iron, that were also led to the nucleation of the voids below the surfaces to promote the fatigue crack. So, it is important like properties are controlled which can offer the desired hardness, desired resistance to the thermal softening at elevated temperature, having the desired microstructure and the desired resistance, desired set of the properties through the suitable composition, heat treatment and the case hardening. Additionally, install the assembly and assemble and install the guidelines properly, so that there is no any misalignment. So, that is all from my side. Thank you for your attention. In this one, initially we talked about the major issues which are caused by the plastic deformation based processes, and then what are the various ways by which the rolling process can get failed, and one typical case study on the failure of the guide pieces used in the rolling process. Thank you for your attention.